Welcome everyone to today's Explainer. I'm so thrilled to have you all here for what is going to be a completely fascinating look into mathematical history. You know, often when we study the history of science, we tend to fast forward straight from the ancient Greeks all the way to the European Renaissance, right? We're kind of taught to view the massive period of time in between as this dark age. Well, today, we are going to completely reframe that era. By digging into the historical texts, we're going to see this period not as a dark age, but as a vibrant golden age. It was the vital, hidden bridge of human knowledge. The math you and I use every single day, it was actively being forged right then and there.
So, let's kick things off with a provocative question, one that every single one of you has definitely thought about in algebra class. Where exactly did the unknown variable x come from? Okay, let's dive into this because the answer is incredible. The great 9th century mathematician Al-Khwarizmi originally used the Arabic word shay to represent an unknown quantity, which literally just translates to a thing. Later on, when these mathematical texts were being translated over in Toledo, Spain, the Spanish language lacked the shay sound, so translators just picked the letter X to represent it. It's actually the exact same linguistic quirk that explains why Don Quixote was historically pronounced Don Quixote. This whole journey, right from the Arabic shay to the Spanish X, just perfectly captures how deeply our modern math is rooted in this era.
Here is the roadmap for today. We'll cover mathematical heritage, the decimal system and zero, algebra and Al-Khwarizmi, trigonometry and geometry, the foundations of calculus, and finally wrap up with lasting impact. Let's get right into it.
Number 1. Mathematical heritage, the golden age of scholarship. So, what actually drove this massive surge in research? Well, it was immensely practical. Precise calculations were strictly required for everyday Islamic rituals. We're talking about calculating daily prayer times based on the sun, mapping complex inheritance laws, tracking lunar cycles, and finding the precise direction of the Qibla. These very real, everyday needs essentially forced medieval scholars to become master mathematicians.
Galileo Galilei totally hit the nail on the head when he said, "Mathematics is the key and door to science." This is a universal truth. Any scientific progress, whether we're talking about engineering, medicine, or astronomy, absolutely required foundational mathematical tools. And during the period we're exploring, those crucial power tools were actively being forged, tested, and perfected across the Islamic Empire. They literally laid the groundwork that later European scientists like Galileo himself would eventually build upon. Let's quickly track how this developed chronologically because the timeline is fascinating. Around 810 the Abbasid Empire founded the House of Wisdom, or Darul Hikmat, in Baghdad. Think of this as a massive, bustling scientific academy where ancient Greek, Babylonian, and Indian texts were all being translated into Arabic. By the 9th century, this brilliant synthesis of global knowledge led to the widespread adoption of the decimal system. Then, and this is crucial, in the 12th and 13th centuries, these heavily expanded texts were translated into Latin and Hebrew in places like Spain and Sicily. This massive transfer of knowledge directly catalyzed the European Renaissance.
Moving on to Section 2, the decimal system and zero, the power tools of computation. Get ready because we are about to look at arguably the most significant upgrade in all of computational history.
And this brilliantly illustrates the immense practical headaches scholars faced before this breakthrough. Just try doing complex multiplication or division using Roman numerals. The number 808 is DCCIVI. Imagine having to write out 888 XXX XVVV. Attempting arithmetic with Roman numerals is honestly like trying to build a modern skyscraper using Stone Age tools. It's clumsy, it's exhausting, and it is highly prone to error. The Arabic Hindu decimal system radically simplified computation, clearing the path for advanced scientific calculations.
But the true magic here, the real game changer, was the revolutionary introduction of zero to enable place value. Before the formalized use of zero, there was a massive, glaring ambiguity in math. If you just wrote an 8 and an 8 side by side, it was incredibly difficult to know the power of 10 associated with each digit. Did it mean 88? Did it mean 880? Or did it mean 808? You just didn't know for sure. The zero acted as this absolutely crucial placeholder. It anchored the entire numerical system and brought absolute rock-solid precision to mathematics.
Section 3. Algebra and Al-Khwarizmi, the father of algebra. Seriously, if there is one single name you take away from our time together today, let it be Muhammad ibn Musa al-Khwarizmi.
The very word algebra comes directly from the title of his most famous book. It derives from the Arabic word al-jabr, which beautifully translates to the reunion of broken parts.
To really wrap your head around this, think of a simple real-world analogy, balancing a physical weighing scale. If you add or remove weight from one side, the balance is broken, right? So to reunite the parts and restore equilibrium, whatever you do to one side of the equation, you must do exactly the same to the other. That elegant logic is the beating heart of all algebra.
His foundational manuscript completely formalized quadratic equations and algebraic multiplication. And get this, the Latinized version of his own name, al-Khwarizmi, gave birth to the modern word algorithm. That means literally every time you write code in computer science or rely on cryptography to keep your text messages safe, you are using the logic formulated by this 9th century genius. His book was so definitively brilliant that it remained the standard mathematics textbook in European universities all the way until the 16th century.
Now, what's really interesting about this historical validation is Leonardo Fibonacci. We know him as a famous Western mathematician, right? Well, he traveled extensively through the Arab world, studied their math, and eventually popularized the decimal system over in Europe. He explicitly noted that the algebra developed by Muslim scientists was far more advanced, disciplined and detailed than anything previously seen from Greek or Indian traditions. This wasn't just a minor improvement, it was a massive, widely acknowledged leap forward.
Section 4. Trigonometry and Geometry, Measuring the Universe. The math we're talking about now wasn't just about measuring flat 2D surfaces anymore. The real breakthrough was spherical trigonometry, literally tracking the curved, complex movements of celestial bodies.
These are the specific heavy hitters who made advanced astronomy possible. Mathematicians like al-Battani and Nasir al-Din al-Tusi essentially built the foundations of trigonometry by creating highly precise tables for sine, cosine, and tangent functions. Meanwhile, the famous Persian polymath Omar Khayyam pushed the boundaries of geometry through his incredibly detailed study of conic sections. It was their combined, genius-level work that allowed for the creation of precise astronomical instruments and celestial globes, mapping out the mechanics of the universe with an accuracy no one had ever seen before.
Section 5. Foundations of Modern Calculus, Centuries Ahead of Time. This one usually blows people's minds. When we learn calculus, the credit almost exclusively goes to 17th century Europeans, like Newton and Leibniz. But, as we'll see, the historical record shows something quite different.
So, the absolutely crucial point to notice here is the timeline. Look at these dates. In the 11th century, Hassan ibn al-Haytham developed a method to find the area of a parabola using a technique that is fundamentally identical to modern integral calculus. Then, fast forward to the 13th century, and Sharaf al-Din al-Tusi developed a method for finding the derivative of a function. I mean, that is the absolute core concept of differential calculus. These brilliant minds were tackling the complex problems of areas and volumes, laying the structural groundwork hundreds of years before the European scientific revolution even began.
Which brings us to our final section, conclusion, lasting impact, the universal language. Mathematics truly is the universal language of our species. The algorithms securing our banking apps today and the geometric principles supporting the bridges we drive over are the result of a deeply collaborative human achievement.
To really put the sheer scale of this contribution into perspective, I want to share a quote from Professor George Sarton, a renowned historian of science. He noted that the number of scientists who left their mark on knowledge and science during the era of Muslim domination is probably no less than the number of scholars of the present era. Just think about that. Over 500 major scientists from the 8th to the 15th centuries fundamentally shaped the world we live in today. It was an intellectual explosion that didn't just preserve ancient knowledge, it completely transformed it into the modern sciences we rely on.
I want to leave you all with this final, provocative thought. We've seen how translating ancient texts from Greece and India in the House of Wisdom, refining them in the Middle East, and then passing them along to Europe built the very foundation of our modern technological world. If that kind of historical, cross-cultural collaboration unlocked the secrets of algebra and calculus back then, what completely unknown frontiers will our current globally connected scientific community unlock next? Thank you all so much for joining me in this explainer today. I really hope you walk away inspired to see mathematics not just as numbers on a page, but as a rich, exciting, and ongoing human story.